Welcome back to the channel, everyone, and happy Friday, or in your case, happy Saturday at 11 in the morning. Today we are going to be covering Snowflake, which is a system that I like because I get called a snowflake pretty darn often. It is a very in-depth paper to some extent, insofar as it covers a lot of different topics, and as a result, I probably can't do it justice because this video just can't be 2 hours. I've got to go to a DJ set in I don't know, a couple of hours myself. And also, I simply just am not that smart and haven't done as much research in this area as I probably could. So eventually, I may end up coming back to this paper when we get to cover some of these topics a little more in depth. But for now, let's go through it, talk about all these concepts at a pretty high level, and yeah. Okay, so as mentioned, today we're going to be covering the Snowflake paper. Now the reason that the Snowflake paper does not have a company associated with it is because Snowflake is a company. So ultimately this paper is describing the data warehouse that they maintain for their company. Cool, so it came out in 2016, though at least according to the paper, they began developing this thing in 2012 and then kind of released it in 2015. So the interesting thing about Snowflake, maybe compared to some of the other systems that we've spoken about so far, is that this is a data warehouse that is completely cloud native. It is built to be run on something like Amazon S3, or not necessarily S3, but just AWS in general, right? So AWS, or at least not at the time of this paper, but I think now Azure and also GCP. And so what they do, and this is why I had a Freudian slip and mentioned S3, is that they separate a storage layer and a compute layer. So we're going to talk about what that means pragmatically, but this actually turns out to be a really, really nice feature when you're looking to get the most out of your money and scale. And so they're going to support this kind of semi-structured data. We'll talk about what that means, but basically the gist is kind of schemaless, at least for part of it. And then finally, also, they want it to be the case that you're doing absolutely zero user tuning. You don't want to have to think about indexes, don't want to have to think about partitioning. All of that is completely transparent to the user, security as well. Cool, so let's start by talking about some motivations. This is a long, wordy slide, but nonetheless, it is pretty important, and so we'll have to address it. Number one is that at this time, cloud is becoming very popular. So what is cloud really at its base? It basically just means you don't have to run your own data center as a company. Someone like Amazon or Google or Microsoft will basically host a bunch of servers for you, and then as a result, you go on their website, provision a bunch of them, put down your credit card, and then now all of a sudden you have a bunch of servers at your fingertips. So this is great because you don't need to manage a bunch of physical hardware, you don't need to hire a bunch of employees that can do that for you. There's a lot less expertise required in this field, and so cloud basically enables a lot of small businesses to get up and running quite a bit faster. And so this is basically extending the philosophy of that, right? Like if you're able to provision all of these servers by yourself, that's great, but you now still also have to manage a massive data warehouse, and managing a data warehouse is not trivial. Snowflake tries to make it so that it is trivial. And so basically what they want you to do is not have to require any tuning whatsoever. You don't necessarily need some sort of database admin or data specialist in order to organize your data. They basically just want you to be able to dump it all in there and then be able to query it very, very easily. And so they want to make it so easy to the point that they even expose basically a web browser interface. You don't even have to download anything. You can just go on the Snowflake website, go query your data, go dump a bunch in there. Makes life pretty easy. And so basically, I guess the gist is that another change here is that in the past, so probably in the early 2000s, maybe late 90s, the majority of the data in these types of data warehouses is internally generated, right? This is all internal enterprise data coming from your application. However, as times are changing in the mid-2010s or the early 2010s, you start to see a lot more of this external data that companies are trying to capture and also log for themselves, right? This is really important for something like machine learning or AI or anything like that in general. And so because of that, you can't necessarily control the schema of it, and so sometimes that data may just switch up on you and you aren't necessarily able to keep up with that. And so Snowflake is built in a manner such that even if there's data without schemas, they try to make it as efficient as possible to query and manage and use down the line. Okay, so the first concept that we're going to cover here, and probably the most important one, in my opinion, in this paper, is going to be this idea of storage versus compute. And in order to cover that, I guess the best thing to do would be to think about how something like Hadoop works, right? So basically, the idea here is that if we have something like Hadoop, right, we've got a bunch of servers operating in some cluster, and the beautiful thing about that is that you have CPUs and disks co-located, right? So for example, we've got a server over here, it's got a CPU, it's got a hard drive. And so what that'll allow us to do is if we have a bunch of data stored in files on that server, we can actually just go ahead and run computations locally. And that's going to allow us to achieve very nice data locality. So when your network links are slow, you can get a lot out of this, and you can perform things like batch computations. So if we're running MapReduce jobs or Spark, it's very beneficial to us to be able to push that computation towards where the data lives. So this is what, at least in the paper, and probably elsewhere as well, I've seen the term used many times, they call this a shared nothing architecture, right? You've basically just got a bunch of different computers, which all have their own CPUs and they all have their own disks, and they are effectively just all operating in the same capacity, right? They're storing some percentage of a table. If we're talking about making a database or a massive data warehouse, they're storing a percentage of the data warehouse, and then any queries on that data are, being run locally and eventually being aggregated somewhere. Cool. And so the idea here is if we are going to run a data warehouse on Hadoop, we're basically doing a bunch of horizontal partitioning of the file data across nodes. So maybe all keys starting with A to F are here, G to N is here, O to V is here, and then W to Z is here. And note that, what this means is we need 4 CPUs and we need a bunch of disks as well. So what are the problems with this, or what basically arises that makes Snowflake take some of the decisions that they do? Well, for starters, when it comes to actually scaling this table, right, because over time you're going to get a lot more data, you're going to need to devote more resources to it. Basically, the idea is that if we add new nodes, we have to reshuffle data, right? This is kind of the concept behind hashing or just consistent hashing in general. Data needs to get reshuffled. And so that is going to basically temporarily degrade our system as it's going to use resources on nodes. So because of the fact that we're taking data and moving it from node A to node B when we expand our cluster, we're now in a slightly degraded state, and it's going to make the system harder to deal with and reason about. The same thing goes for online upgrades, right? If we take out a portion of the system, now all of a sudden we basically can't query that partition. Now, of course, this data can and should be replicated, but it definitely makes things harder to think about. And again, it just points to the fact that the system is going to be generally degraded for a bit, right? Like, if there are 3 replicas serving some data and I take out 2 of them, so only 1 is now standing to serve it, now we've just lost quite a bit of read throughput potentially. So that's going to be a problem as well. So now let's think about what happens when we're actually trying to run Hadoop in the cloud, because this is what a lot of companies are doing, right? They have their cloud architecture, they don't want to manage a full data center, and they now want to run Hadoop to basically have some sort of big data warehouse, and maybe that's kind of using Spark or something like that to return query results. So basically the idea here again is that you need to be provisioning servers. And so let's imagine that we have all these servers, right? Each one of them has a set amount of disk that you provision with it. And the idea is as we keep scaling our table, we're doing all this partitioning, we're rebalancing, and maybe we're storing a ton of data, right? Because we purchased a certain amount of disk with our servers, and we need all of that to store our data. At the same time, when you do purchase that amount of disk, you also have to purchase some amount of compute power with it as well. And if all of that data is just sitting there, let's say it's midnight and no one's working that day and no one is running any queries, then all of a sudden you're basically just wasting a bunch of money provisioning all these servers and not actually using any of your compute resources. On a similar tangent, there are certain times where you're using a ton of compute resources, but you don't actually have a lot of data. Right? So let's say we're running expensive batch computations or complex queries, but our data set is fairly small. Then that would be an example where you need a lot of CPU, but you don't need a lot of disk. And so basically what we would like to be able to do is to actually scale out these 2 kind of independent axes in a way such that we can better use our actual budget for data and be more efficient with that. And so what Snowflake chooses to do, and they're not the first ones to use an object store here, but they do it, and it's certainly more popular as a result now, is that they use an object store for the storage layer. So they're using something like Amazon S3. Now, to tell you the truth, I've done research on this topic like 10 different times, and I can't really figure it out why exactly it is, or how exactly it is that S3's architecture works under the hood. I have a general idea of it, but I think the gist is, 1, it's super elastic, right? You can store pretty much infinite stuff in there. 2, if there is any rebalancing or repartitioning, it's done completely transparently to you, and it doesn't seem to have any impact on performance. And number 3, is that you're not paying for compute, right? You're completely paying for storage, and that is very, very important to know because it allows you to basically store as much as you need or as little as you need and pay for that accordingly. And so this is very nice because now all of a sudden, we put all of our data, right, all of our files of basically table data in S3, And then what we can do is provision a second set of servers specifically for the actual compute of running the queries on that data. And so that is going to be this separate set of servers. So let's go ahead and describe this architecture at a high level. Basically, Snowflake has 3 different layers. One is called the cloud services layer. I won't talk too much about this, but think of it just as metadata, right? For all of these files in S3, we need to know which files are comprising which tables. We need to know which users are responsible for which files. There's a lot of encryption data because everything is ultimately stored encrypted. I won't talk about that too much, but they have a fairly complicated system of basically encrypting and over time re-encrypting the data to ensure that your encryption keys aren't too stale. So that is the cloud services layer. From what I understand, it's completely fault tolerant and it is completely ACID compliant. So it's probably going to look something similar to what we see in certain other of the data warehouses that we covered, where you're probably using something like a geographically replicated like Paxos store or something like that to ensure all of that. Because at the end of the day, your metadata layer oftentimes is not your bottleneck, right? It's very important that it's ACID compliant so that you can add files in bulk and then switch over your pointers, delete them as necessary. But I'm not going to devote too much time in this video talking about it. A, because the paper doesn't talk about it, but B, I think the more interesting piece are these 2 layers down here. So number 1 is S3. We already spoke about this, right? We've got all of our immutable table data files over here, and they are going to be stored in a column-oriented / hybrid format. So hybrid format really just means it's column oriented, but every few rows you break them up into their own file. And so this is kind of the idea behind something like Parquet. Snowflake does end up using their own proprietary file format, I believe, but I think it should look very, very similar to Parquet in terms of what it's actually doing. Cool. And then the layer that we haven't covered just yet over here is called the virtual warehouse. So the virtual warehouse is something that, again, is something you provision within Snowflake, and it's basically a small cluster of worker nodes over here, where each worker node can basically run together within a query, read some subset of S3 data, perform any computations that it needs to on it, potentially shuffle data between the workers, and then ultimately return that right back to the user. Now note that you may have a bunch of different virtual warehouses, right? Because maybe company 1 is over here using this virtual warehouse. Maybe company 2 is over here using this smaller virtual warehouse. And so these virtual warehouses come in like predefined sizes. The reason Snowflake does that is so it's easier for customers to pick one. But basically imagine, there's like a small virtual warehouse, there's a medium one over here, there's a large one over here, and different companies might provision them based on the needs that they have. You could even provision different ones within different business organizations if they have different budgets or something like that. Cool, so let's talk about virtual warehouses in a little bit more depth. Basically, this is a collection of worker nodes that are going to actually run your query computations. Now, if you recall from our Dremel video, this almost feels conceptually pretty similar to that, right? Like Dremel was basically you have a bunch of query executors that are caching data, they're reading from some sort of file store, and they're running the computation there and passing results between one another, right? Those Dremel executors were completely in memory and they were doing as much caching as possible. So basically, it's the same idea here, right? Reading from S3 is fairly expensive because that's a bunch of data that's stored on disk. And in addition, you're no longer actually getting good data locality when you run your computations, because S3 is a completely separate storage system to any of these virtual warehouses. You have to actually load the data in from S3 over the network and then perform compute on it. And so that is fairly expensive, right? Now, it is the truth that in the last few years, especially in the 2010s, network speeds have gotten a lot faster. And this is less of a bottleneck now to do this type of thing than it was in the early 2000s, which is why you see this Hadoop model being so popular at that time. However, in order to kind of mitigate the cost of reading files over S3, because these files are still fairly big, what we're going to do in the virtual warehouses, like I said, is every single time that we read data, we want to go ahead and cache it locally. And so we're going to go ahead and do that. And then we're also going to use LRU replacement, because at some point we're going to run out of storage there, right? So we're actually caching all of that data on our local disk, note local disk, not memory, on our virtual warehouse workers, and that way we're going to be able to speed up quite a few reads. So the idea here is that, if we're going to be performing all of this caching, it would be great if we can improve our cache hit rates. And the way that you do that is by having the same worker nodes of each virtual warehouse querying the same files within S3. We can do that pretty easily. The way that we do that is just by taking the hash of the file name and always sending it to the same virtual warehouse worker. Cool. You can do that, like I said, via consistent hashing. This is just going to ensure that we get relatively even rebalancing or relatively even distribution of the files to virtual warehouse nodes. And so if a virtual warehouse has 3 nodes and we add one more, you don't actually have to do any shuffling, right? This was a problem with Hadoop insofar as when we add an additional Hadoop worker, we have to shuffle data between them so that the data is evenly distributed for computation of queries. That being said, for virtual warehouses, we're just caching data. So all you really have to do is add the node. We account for the fact that, basically certain files are now going to different worker nodes. But nothing actually happens until they actually start reading data from S3. And then over time, if certain nodes are holding cached data for files that are no longer relevant to them, they're just going to drop that via that LRU policy. Cool. We're going to talk about these a little bit more because this is kind of the bread and butter of Snowflake. It's why it's going to work well, or perhaps why it's going to work poorly as well. So a nice thing about virtual warehouses are that they're effectively stateless, right? Like, because they're only really doing caching, and because caching is not necessary for correctness, it's necessary for performance but not correctness, you can basically kill these things off and add them back as need be, right? And that consistent hashing mechanism is going to make sure that everyone is caching the right stuff. And so what's really good about this is it's super, super important for elasticity. So let's imagine, like I said, it's midnight, no one's using our system. We could basically, on some sort of schedule, say, hey, we're going to cut our virtual warehouse size in half. Let's, cut out half the workers. We're not going to pay for these anymore, and now all of a sudden we're saving a lot of costs. On the contrary, during particularly busy periods, maybe it is, right after lunch and everyone's back to doing work, they're feeling productive, you can basically go ahead and add more compute to that virtual warehouse cluster. The nice thing about this is if you're going to run all of those queries anyway, you're getting billed by CPU hours. So basically you're getting a bunch of extra performance effectively for free because of the fact that you're just getting billed by the amount of compute that you were doing, not how many servers you had provisioned. Like, as long as you have the same amount of servers provisioned for half the time, let's say you double the amount of servers and use them for half the time, you're paying the same amount of money. And so effectively you're getting this incredible performance speed up without having to manage any of that hardware yourself, right? Like, as far as you're concerned, when you're using a cloud provider, they may as well have unlimited hardware for you. And so this is something that you can pretty much just do and scale up as you need. Another thing is that all of these table files that we're storing in S3, right, all of this column-oriented data, it is completely immutable. You don't have to worry about any sort of contention or locking or anything like that. And additionally, it means there are no external impacts, right? So even if we were to update or write new data into our table, that is going to lead to a new S3 file. It's not going to modify any existing ones. So we don't really have to worry about external effects very much. If something or some sort of operation dies midway through, we can just go ahead and retry it. It is not the end of the world, and this makes the system a lot easier to reason about. Additionally, all the memory on the virtual warehouse workers themselves, like I said, is devoted to query computation, not caching that S3 table data, right? That is all going to be done on local disk. When the writers of the paper were evaluating this decision, they basically said, listen, we could, have basically an inner cache of our locally cached data, right, where you take it from disk and also cache it in memory to make those reads even faster. But ultimately they decided, okay, you know what, we have all this memory. This memory is better served for actually performing our computations rather than caching a bunch of disk data. We want as much of that available for ourselves as possible. In the event that we were to run out of memory on this virtual warehouse worker while we're doing some sort of computation, then basically what you want to do is you can either spill to local disk, right? So for example, let's imagine we're running some operation that is, counting distinct elements, and that set of distinct elements gets too big. We can now store it on local disk, or we can also store it on S3, which effectively means that we have infinite storage when it comes to performing computations. Obviously, things are going to get a lot slower, but it also does mean that you're not going to have any out of memory or any issues like that where things just crash. And then finally, stragglers are something that we've spoken about a lot during this deep dive series, which is basically when you have a bunch of distributed workers, one of them, for whatever reason, probably hardware issues, could just be a lot slower than others. And so if this is the case, what these workers will do is they'll say, okay, I finished my task. Can I steal any work from the guy who's being really slow? Maybe you can offer me one of the files that you haven't read yet. The slow guy will then say, oh yeah, for sure, go ahead and read that. And then the worker that stole that file will now go to S3, do the work themselves, and send all of that result downstream. Okay, so the first thing that I want to talk about when we really start getting deep into this one is going to be the data file format. So this one is very similar to Parquet, which I've made some videos about on this channel, so hopefully this shouldn't be too new for those of you who are watching this. But basically the idea here is rather than using row-oriented storage, we're going to be using column-oriented storage. So row-oriented storage is very, very useful for transaction processing, right? So if I'm using a shopping cart and I'm a user making a bunch of ad hoc operations, ideally I want to see the entire database row at once. I tend to care about that. For analytical queries, we're often running aggregations over just a small subset of the columns, and so it's better to actually get good data locality by storing those columns together. So you can see here if maybe an OLTP database is storing their data like this. We've got row 1, column 1 is stored next to row 1, column 2, row 1, column 3, row 1, column 4, right? This is one row right here. On the contrary, we would have all these row groups, right? So you take a subset of the rows and you store them in a file, and then you actually store the data from the same column together, right here. Another really nice advantage of using this column-oriented storage is that you can perform compression, right? Since all of the columnar values are generally more similar to one another, especially if they're numbers or something like that, which is often the case in a database like this, you can compress the shit out of them and as a result just store quite a bit less data, which is quite nice. Another nice thing about having data that's very similar to one another be next to one another on a file is that we can basically perform the same computation over and over and over again, and perhaps, if we're really lucky, even in parallel. So for those of you who are familiar, there's something known as SIMD instructions. Think of them as basically CPU CPU assembly instructions that are able to process the same operation in parallel. So you're basically, maybe you have like a 16x SIMD register. What it means is that you're doing the same SIMD operation 16 times over in one CPU clock cycle, and so you're basically 16xing your performance. And so these are things that you really have to start taking advantage of when you're trying to build a super fast analytical warehouse. Oh, and then finally, before I gloss over it, each file has a bunch of metadata, which is located in the header of that file. That metadata is useful for something known as projection pushdown. Well, not for the projection pushdown, more so for the predicate pushdown, which we're going to touch upon in a second. Cool. So file immutability. Like I mentioned, all of these files that are living right here, completely immutable. When we're updating data in Snowflake or we're inserting new data, you are not actually going to be modifying those files. In fact, in S3 in general, you're literally not allowed to modify a file. This is in contrast to something like Hadoop, where you have that append operation to add to the end of a file. In S3, once you write a file, it's completely immutable. You can read it, you can read a sub-range of bytes from it, but you can't touch it after that. So when we're actually doing inserts or updates in Snowflake, basically we have to go ahead and create new files. And so like I mentioned, we have this metadata layer. The metadata layer is pointing to which files actually comprise the database. And so when we're going to create a new file to include it in our database, we can basically atomically say, oh, you know what? We're no longer including this file in our database. Now we're including this other one. The nice thing about that, though, is because the old file was immutable, it gives us the opportunity to perform all of these, kind of nice properties in the database. One of which is you can now read from consistent snapshots, right? Effectively, we just read from the old file. And even if we have a very long running operation, that old file may get overwritten, but we're still going to use that because, effectively it's going to give us a consistent view of our data. It also means that we don't have to do any amount of locking because of the fact that, everything is immutable and we have these copy on write semantics. So because of the fact that we're doing MVCC, if you recall, that's multi-version concurrency control. Every single version of the data has like some sort of timestamp associated with it for each file, and so we get these consistent snapshot reads out of a result of that because we just provide the timestamp that we're reading with, and then we're basically reading all data before that timestamp and keeping it around. So even when data gets overwritten, we'll keep it around for some amount of time, maybe a few days, and then eventually we'll drop it. Cool. Another nice feature of having a bunch of immutable files is that you can easily copy a table to a new table by basically just going to the metadata database and saying, hey, create a new table and have all of these pointers pointing to the same set of files. Now, if someone on the new table wants to overwrite some data, right, and you don't want that change applied to the old data, that's fine because files are going to be copied on write. And so you just have the new table pointing to that new file in the metadata database, and then the old table continues to point to the old version of the file. Indexes. Now, this is a very interesting part of the database that I found interesting, right? Because if you think about like our big table paper, for example, everything is globally sorted by some sort of key. On the contrary, in Snowflake, Snowflake is like absolutely not, no indexes whatsoever. Couple of reasons for doing that, right? So for one, just like as a general kind of dogma or philosophy behind Snowflake, they don't want to do any performance tuning. And technically, an index, even though it's not so hard to just like go and click make index on blank field, that is performance tuning, right? It involves having some knowledge of your query patterns, how a database is going to work, and they just don't want to deal with that. So they want to make it as seamless as possible for you to use their database, and as a result, they say screw it, no indexes. In addition, at their scale, dealing with indexes is just pretty tough, right? You have to store things multiple different times. You have to basically globally sort your data, which is also going to be tough. It makes insertions a lot harder because now you have to overwrite many different files at a time. And it just relies on many random data accesses, which is just going to be fairly slow on S3, because if we're doing some sort of binary search, we have to go to all these files. We have to like look at their headers to see what range of keys they contain. Then all of a sudden, when we eventually reach a file where we think we have it, we have to decompress that data and then do another binary search within that. They just don't want to deal with it, and so they don't support them. Okay, the next thing that we're going to talk about is predicate pushdown and projection pushdown. So projection pushdown is pretty simple. This is kind of the benefit of column-oriented storage, right? Which is if I only need to access a subset of the columns, when I go to S3, I basically say which columns I want to access, and I'm only going to read the data for the columns that I care about, which is going to make things a lot faster. If there were 1,000 columns in my table and I only want to read 2 of them, this is going to show us a significant performance increase. Predicate pushdown, on the other hand, is something like this. Let's imagine we want to do the following. Select X from our table that we've written out below, where X is greater than 20. So we've got the following table right here. It's got 2 columns, X and Y. And as you can see, X has these values 3, 7, and 12. And so what our file format is going to do for us is whenever we write a file, it's going to keep a little bit of metadata regarding the values within that file. So in this case, we have a min-max. So X is definitely going to be between 3 and 12. And so what that means is when we're actually reading this data, we can read just the header first because we don't have to do any decompression. We read just the headers. We see, okay, X is between 3 and 12 in this column. Let me not read these bytes. So it's quite fast to read headers because that's very little data, but it is quite slow to read the actual column itself because A, it's a lot more data, and B, you have to decompress it. Similarly, since we're only selecting X here, we look at this Y column and say, all right, well, we don't want that because, that's a Y column. We look over here, we see min 6, max 32. Ooh, we are going to have to read this column and decompress it. And ooh, again, this is a Y column, so we're not going to read that. We're going to cut that out. So just like that, we basically pruned is the term that Snowflakes uses to basically describe avoiding having to do a bunch of reads. We pruned 3/4 of our data. And so that is how Snowflake tries to be as fast as possible. They also do something known as dynamic pruning. So let's imagine we're doing an inner join, right? We're joining 2 tables, T1 and T2. We're joining them on this field called ID. And for now, I'm just going to assume that ID is actually the only column in both of these tables. So let's say that this goes ahead and does a hash join. So we've got T1 over here. And so if you recall from our hash joins, typically what we'll do is we'll take the smaller table and we'll build a hash table from it, right? So, you'll have ID colon data, and we'll maintain some sorted hash map in memory. Cool, or potentially on disk as well, but ideally in memory. So we're going to build our hash tables from T2, and when we do that, we're going to basically do that on some workers in our virtual warehouse over here. So we're going to see, okay, well, maybe on T2, we've got these 2 virtual warehouses because it's a big enough table that we had to basically distribute this hash map that we ultimately built. So on this worker, we see, okay, here we've got 10 and 5. These are the IDs that live here. And here we've got 97 and 4. So again, we're going to do this same idea of doing like the min and max of both columns. And so we can see that, all right, this one basically only has values between 5 and 10 for ID. Let's imagine, same idea, T1 is bigger. So we're going to split up the key set such that we have 3 workers in our virtual warehouse that are reading from this table. And so let's say this guy now is responsible for finding all of the join information for data that includes 14, 97, and 56. Since we know that 14, 97, and 56 are all greater than number 10, we can basically skip checking node A. And so doing this type of thing is also another nice type of notification. So sorry, to be clear, this is node A right here. We know that there's not going to be any viable joins between them, so we can skip actually sending all of this data over the network over here, and that's going to speed things up quite a bit. The next thing that Snowflake does is it's going to perform push-based execution as opposed to pull-based execution. So the question is, what are those terms? We've never mentioned them on this channel. This is a bit complicated, and I'm going to do my best to explain it as well as I can. I'm also going to link an article about it that I severely plagiarized. But basically the idea here is that databases in the past use something known as pull-based execution. So in pull-based execution, imagine we have a few different database operators, right? We're doing like a select distinct field name from a table where x is greater than 20. So similar query to the one that we ran over here. Select x from table where x is 20. Maybe you add a distinct right here. So that's what we might be representing with the following query plan. So basically, in a pull-based execution model, we can label all of our operators in this tree or in this graph, and every single thing that we're going to do is basically one operator is going to say, okay, I'm the distinct operator. I need some data. Hey, project operator, go give me a row so that I can determine whether or not it's distinct and should return it. The project operator is going to say, okay, well, now I need to get data, and how can I project this data to the field X that I care about unless I have data? So in step 2, the project operator is going to ask the filter operator for a row. In step 3, the filter operator is going to say, okay, well, how can I filter this data down if I don't actually have anything to filter? Why don't we go ahead and scan from the table? So let's say, the scan operator returns element 10. The filter operator is going to say, oop, you know what, I'm cutting that out. That's not greater than 20. Maybe now scan is going to return element 25. Filter is going to say, okay, you know what, that works. I'm going to return this back up to the project. The project is going to say, okay, I'm going to keep element 25 because I'm just projecting that field to its column value, which in this case is 25. And then distinct is going to say, hey, have we seen this guy before? Either we have or we haven't. So we have this whole iterative process where basically every operator goes downstream and then asks for another row from it. So if we want to think about this guy conceptually, it's basically a bunch of functions that are calling a bunch of other functions. So in the distinct operator, we've got this concept of have we seen a current element? But the current element that we're getting is actually coming from our project operator. And our project operator is just saying, okay, take our current data and map it to some particular function. And in order to actually get the current data, we have to call our filter element. So we basically have this big nested call stack of functions that we're going to be doing to get our eventual result. So what are the drawbacks of pull-based execution such that we deviate from it here? Well, number one, we've got bad handling of reused data. So in SQL, you can have a with clause, right? So, with x as blank, some sort of SQL query, and then you reuse x in multiple places down the line. So in this case, we actually have intermediate results that we would ideally only like to compute once. The problem with pull-based execution is that inherently every upper operator is going to basically just be, every upper operator is asking the lower operators for data, and then the lower operators are recomputing that. So let's imagine we have some sort of join, and the join is on we scan some data, we project it in one operator, we filter it in the other operator, and then we join those two together. What's going to happen now is the join is going to ask project for data, project is going to ask scan for data, join is going to ask filter for data, filter is going to ask scan for data. And so now we're going to be scanning the table twice, and that is going to be fairly inefficient. I guess you could say, oh, maybe we can go ahead and materialize this thing so that we have access to it later. But the point is, just generally speaking, in a pull-based execution result or query plan, we are not able to really have a good conception of what the eventual data flow is in a way that we can really be smart about materializing it. And so again, this may end up with us naively scanning the table twice, which is going to be inefficient. Number two is that we're doing something called tight loops. Now this, I'm really starting to get hand wavy because I can't even necessarily confirm that this is 100% what they were talking about in the paper, but to the best of my knowledge, I think it is. A tight loop is basically when you're running the same loop over and over and over again, and you're never yielding to like a context switch, right, to switch to another thread. And so in this case, because we have this iterative process, right, and I draw it out right here, we're basically just jumping down a call stack, and then we're coming right back up the call stack. So there's never really any point in this kind of model where we're actually yielding control for a context switch. And so perhaps it's going to be the case that we end up getting bad CPU caching efficiency. So why would that be the case? Well, let's think about the distinct operator, right? The distinct operator is really just going to be maintaining a set of elements. And we have to maintain a set of all the elements that we've seen, some sort of hash set. And we need that quickly accessible to be as fast as possible here. So it'd be great if we could have that in like our CPU registry cache. So maybe our L1 or our L2 or our L3 cache or something like that. So if we're running the distinct operator over and over and over again, we know that we're going to keep using that scene set, and we're going to keep that set cached. However, if we run the distinct operator, and right before we actually run it, we then jump to the project operator, and right before we run that, we jump over to the filter operator, and right before we run that, we jump over to the scan operator, I bet we're probably going to have some amount of cache thrashing where basically all of the relevant values that we need to have locally cached to us keep getting replaced by the downstream operators and then keep getting replaced when you go back up the chain. So I could see that being a problem here. Yeah, a bit hand-wavy on my part, a bit speculative as well, but I think that is what they're implying in the paper, and I'm more than willing to have anyone go to this section of the paper and try and fight me about it. Cool. On the contrary, we also have push-based execution. So push-based execution I think is pretty simple to reason about. Imagine we have the same exact query plan that we had for before. In this one, rather than basically waiting for upstream operators to say, hey, give me data, you basically just start doing compute eagerly, right? So in the case of the scan operator, it's going to say, all right, I know I have to scan this table. Why don't I just go start sending data to the operators above me? So right off the bat, it's just going to start reading from the table as soon as possible. Doesn't have to be it doesn't have to wait on the filter operator to trigger this, and it just starts pushing data up here. Same thing goes for filter, right? Filter is going to push a bunch of elements as it's getting them from the scan table up to the project thing. Project is then going to do the same thing to the distinct operator. Now, I think an interesting thing here is how it pertains to intermediate results, right? Because the same thing in this query plan over here, if I go over here and we represent it, so this is our scan, this is our project, this is our filter, and this is our join, this guy is going to start up and it's just going to say, oh, you know what, let me just go ahead and push the results, right? So you're only doing that work once, you're pushing it twice, and now your work is not going to be duplicated. Also, just in general, if you think about it conceptually, this is probably a little bit easier to schedule on a distributed basis because each thing is kind of operating more independently, right? You're not waiting for a bunch of network calls being like, hey, now go do work, now go do work, now go do work. It's just saying, I can do work, I'm going to push that result in batch to the operators above me, but you can operate a bit more independently here. Cool. So a couple of potential disadvantages to push-based execution. For starters, some operators are going to be poorly suited for it, right? So let's imagine the sort merge join. Another thing that we've spoken about on this channel before, way back in our concept series. The gist is if you have two data sets that are sorted or indexed the same way, you can really efficiently join them without having to basically materialize any sort of hash table in memory because they're ordered the same way, right? So as long as I keep like 2 pointers, this is effectively a 2-pointer algorithm, I can say, all right, these guys are the same right now. Is this guy the same? No, it's not, so I'm not going to increment my pointer here. Is this guy the same? Yes, it is. I'm going to increment my pointer here. Oops, same ID, so we need a join between these two, a join between these two. Increment my pointer again. Oh, join between these two. All right, now a different ID, so we increment our pointer again. Oh, wait, join between these two, join between these two. Oh, wait, increment our pointer again. Join between these two, join between these two, join between these two. So sort merge join is not going to work that well in push-based execution because you literally need to process like one element at a time, and you need to go to your below operators and be like, hey, give me the next element that I care about, because otherwise you can't traverse them in lockstep. You're just going to have one returning like a bunch of this data, and then the other guy returns this guy, and you're like, I don't know how to merge these together. That makes absolutely no sense. Number two is going to just be limit clauses in general. If you want to say select star from a table, limit to 10 results, well, how is our scan operator going to know how many results to return? If it's a simple query where it's like select star limit 10, sure, maybe you can pass that information down to the scan operator and it knows to limit the size of the results to 10 things. But if you're doing some sort of joining and you don't know the actual final size of the data set or how many results there will be, you basically do as much work as you can downstream And then eventually at some point you're just going to have to go to your scan operator and be like, hey, you can stop now. We've got 10 results. We're good. But obviously that's going to result in using a lot more compute than you would have done if you were doing poll-based execution. Cool. As far as query optimization goes, this is something I'm really not going to dive in too much into this video because A, they don't cover it that much in the paper. B, it can probably be devoted to like 10 different videos, and I'm just, not knowledgeable enough about it. I don't want to act like I know a bunch of stuff that I don't, and that wouldn't really be fair to you guys. So we're going to talk about query optimization subsequently, but I guess at a high level, query optimization is, we take a SQL query, which is declarative, right? You're not exactly saying how you want to do your computations. You're just saying the final format of the data that you want, and you are converting it into a bunch of concrete operators, right? So in the same way that we have a query plan over here, we are going and creating that. And so the interesting thing is there are many different query plans that you can create to get the same output of data, and some of them are going to run a lot faster than others. Think about things like join orders, stuff like that. It makes a big difference. And so Snowflake is going to do something known as a top-down approach, where basically it starts from the ideal end state of the data and then kind of traverses through a bunch of potential approaches and tries to use heuristics to estimate which one is going to be the fastest. Now, a couple things that make this a little bit easier on Snowflake than in other places. For one, there are no indices, which gives us just quite a few less possibilities to consider, which makes query optimization a little bit faster. Number two is that they postpone many decisions in order to make them a little bit better for execution time. So for example, join order, they'll actually wait until, let's say, they scan both tables to determine join order to see which one is bigger and which one is smaller. And so even though this might be a little bit slower than if you just guessed it right from your query optimizer, in practice it makes performance a little bit more predictable because it means that you're always going to be making the right decision. There's never going to be cases where your query optimizer is just completely wrong and then all of a sudden a query takes much longer than it needs to actually run. Cool. Next thing we're going to talk about is semi-structured data. Wow, I did not think this video was going to go as long as it did, but there is a lot here to talk about. So basically, like I mentioned, when you're running a system and you're trying to incorporate external data, a lot of it might be stuff that you don't necessarily have a schema for in advance, and as a result, you still want to incorporate it into your systems and query it efficiently. So basically, another nice thing about that is, let's say it's even within the organization, you don't need to have a bunch of cross-organization coordination in terms of like a new data format, right? Because that could take a while. If you have a data pipeline that's processing data from one format to another, and the input format changes, now whoever's running that data pipeline has to change their pipeline accordingly. So what Snowflake does, which is actually quite interesting, is let's say you have some sort of nested column, because it supports a bunch of JSON. So let's say you have some sort of nested value within the JSON, and it is present in the majority of the records. Snowflake will actually automatically detect that. It will extract that as if it's its own column, and then it will do the normal column-oriented storage, compression, all that fun stuff with it, which is really cool. And so basically, it'll also compute metadata for predicate pushdown, which is going to allow us to, perform scans where we care about the value of this column quite a bit faster. So let's go ahead and show off how that's going to work. Imagine we've got two row groups, same idea as before, and we care about the field person/address/zip code. Now in row group 1, it's present in the majority of records. In row group 2, it's never present, right? 0 out of 100 records. So in row group 1, we're going to go ahead and basically extract that out into its own compressed data. It's got its own file. And so, let's say these are the zip codes. We'll compute a min and a max for it. So this is going to make scans over this data a lot faster when we care about the value of the zip code field. In row group 2, we're obviously not going to extract it because it literally doesn't even exist in that data. The question is, let's imagine we're running a query like follows. Select person.zipcode or person.address.zipcode from table. So we have to read over row group 1, which we can do by, just reading this compressed data right here. And then we also have to check all the values in row group 2. The thing is, this field isn't present in row group 2, but because we don't have this, metadata for the field, because we never created any column-oriented storage for it, how are we actually going to know that we can skip over row group 2? What Snowflake does is it actually creates a Bloom filter. And what it'll put in this Bloom filter is actually the path name of the field. So person/address/zip code. If it was present, they would put it in the Bloom filter. Because it's not present, it's not in the Bloom filter. So if we're lucky, we're going to read our Bloom filter. The Bloom filter is going to say, actually, I've never seen person/address/zip code. That means we don't have this record present anywhere within the field, and as a result, we can go ahead and skip it. Now, of course, Bloom filters are not deterministic, right? It'll deterministically tell us when a certain field path is not in a row group, but it might also erroneously tell us that a certain field path is in a row group when in reality it isn't there. They're probabilistic data structures. Okay. I think we're almost getting there, but now we're going to talk about optimistic type conversion. So optimistic type conversion is a pretty simple concept. Let's imagine that we have some sort of date time field, and it's stored as, let's say, an integer or maybe a long for millis since epoch, so millis since 1970. Let's imagine that pretty much in 99% of queries, someone just runs select date of epoch millis from the table. So we have a bunch of read-dominated workloads, right? Like any data warehouse is being read a lot more than it's being written to. And so this conversion is being run a bunch of different times, and it's just wasting a bunch of compute. What would be easier is if we could actually just pre-compute that value. So when Snowflake detects a situation like this, it'll actually automatically create another column where we actually have the computed value. So epoch millis underscore date, let's say, for example. So the one problem here is that it may incorrectly assume that just like a column of a random grouping of numbers is a date and perform that conversion. And if it does ever randomly assume that and do so erroneously, you can always just reverse the computation at query time. So again, now you're going to have to do more computation, which sucks, but at least your data is correct. Or what they may do is store both epoch millis and epoch millis underscore date. And if you're not running that date conversion in your actual query, then it'll just go ahead and return the value of the original column back to you. Okay, we made it. Wow, I didn't think we would ever get here, but we've done it. My head hurts a little bit. So, in conclusion, basically, the architecture of Snowflake is highly dependent on the fact that it is cloud native, right? All of these decisions have been made because of adaptations in basically the cloud computing space and also just the data space in general if we're talking about these semi-structured columns. So basically, we've got these powerful tools. The idea is we don't want to have all of our clients configuring them constantly. It's just going to make our lives and their lives harder. How can we make just like a generally really, really good data warehouse where you can squeeze out the most performance for the budget that you've got? So the way that we do that is by allowing scaling disk and compute independently. What this means is that we want to be using something like an object store for all of our actual storage files or our Parquet files or our Snowflake proprietary file format or whatever it is. So we use S3 for disk. We use these virtual warehouses for compute. As a result of S3 being slow, we need to cache stuff on virtual warehouses. We do all of that consistent hashing. We try and get as good of a cache hit rate as we possibly can. And in addition, we also want to minimize the amount of S3 data that we're reading on a given query. We do that via pruning, right? We have all of this column-oriented metadata. And in addition, because things are column-oriented, we can skip out on the columns that we don't care about. So minimizing the actual volume of data that we read from S3 is super important as well. And then finally, this is also going to be very useful for semi-structured data. Like I mentioned, we can take semi-structured data, convert it into our column-oriented format, and then run more efficient queries on those columns as a result of that. We get to compress that data. We get to have all of this metadata information that allows us to prune based on that column value, and this is ultimately going to be super useful. And then finally, like I mentioned, the beautiful thing about these virtual warehouses is that they're completely elastic, right? They're stateless, they're super easy to scale up and scale down, and if you have particularly busy periods, you can just go ahead and add more resources and be good to go. Anyways, guys, I hope you found this video useful. I know it's a long one, a lot of new concepts introduced as well, but I think I really enjoy papers like that because, I'm doing like a massive depth-first search here in terms of the subject matter that I care about, and so this now gives me a bunch of different topics that I know I have to research further, and I'm looking forward to doing so on this channel. Anyways, I hope you all have a great weekend, and I will see you in the next one.